Hello, and thank you for coming to my e-presentation. My name is Josh Roy, and I'm presenting on some recent work that I've been working on. It's titled Visual Transfer for Reinforcement Learning via Wasserstein Domain Confusion. So currently, artificial intelligence has a lot of capabilities. We've been able to do a lot of great things in this field, such as playing chess, Go, both at a superhuman level, and we've been able to make a lot of progress in video games, such as Atari. However, what we want to do is have artificial intelligence that can do things like clean our houses, serve us food, or drive our cars. And this seems to be a capability we don't quite have yet. So the difference between these two is generalization. All of the tasks that I've presented that we want to do are all not individual tasks. It's not play this one game. It's not clean this one house. It's not drive this on this one highway. It's drive on any highway anywhere in any country versus playing only Space Invaders. And so generalization is the challenge that we're facing right now. So as with all things, we start in our simulated environments so we can train our agents and test our agents, see how well they do. This is a game from the OpenAI ProcGen set, and it showcases the same game with two different visual components. Now, to a human, both of these look different, but it's obvious how to play both of them. You move your agent, your character over here to the right to get the coin, probably avoid the enemy-looking blob. Maybe the boxes get in your way, but their height doesn't really matter too much. However, to an artificial intelligence, a reinforcement learning agent, trained with a neural network, if you train it on the left game, it cannot play the right game. And so this is a bit of a problem, and it's primarily a visual problem, and that's the problem we're trying to solve. This stems from the fact that artificial intelligence neural networks don't actually know what things are like humans do. A human looking at the game on the right and the left will be able to easily play the game on the right. Keys are good, enemies are bad, jump on platforms, but to an artificial intelligence, it looks much like the game on the left. If you train an AI on both the left and the right game, it'll do perfectly well at both. Humans, however, will fail at the game on the left, the pixelated blobs that really mean nothing to us. So this is the source of the problem. Now, we're concerned with reinforcement learning agents, which means we have an agent that gets some information about its environment called a state. It takes an action, which then triggers some update in the environment. You can imagine Mario, jumping or walking forward would change your video game, your environment. And that will produce the next state, in this case, the next image screen, as well as a reward. In Mario, the reward is probably for getting to the end of the level. And the goal of such an agent is to maximize its expected reward. Now, more formally, we're going to talk about Markov decision processes where you have states or pictures of your world, actions, which are the actions you can take, and these are both sets, finite, a reward function that maps from each state to a real number that the agent is trying to maximize, a transition function that determines how the world moves to the next step, and these together will make your Markov decision process. However, as we're talking about transfer, we're going to talk about block Markov decision processes. These have the same actions, the same rewards, and the same transition function. They also have ground truth states, which are exactly the same as the states we were talking about earlier, maybe the position of the goal, the position of your agent, but notably, they're not images. And then they also have observations, which are rendered through an emission or observation function. This maps from your state to an observation. So you can think about the internal RAM state of an Atari game versus the image that you actually get, that your agent gets to see. Now, when we transfer, we're transferring between two different block MDPs that are sampled from the same family. These two different block MDPs will have the same actions, rewards, transitions, and ground truth states, but different observations because they differ in an emission function. You can think about earlier how we had a dark background versus a light background. That would be a difference in observation, but not actually ground truth state, like the position of your agent. Now, OpenAI has released a set of environments called ProcGen, which is supposed to benchmark generalization in artificial intelligence. It contains 16 different environments. They're procedurally generated, focus on generalization, which is also known as transfer learning, can be known as feature learning, state representation. It goes by many names. Notably, for these experiments, we've modified them into block MDPs. So each domain sampled from an environment will actually have the same underlying ground truth states, but have different observations and different emission functions. And the goal is to train in one such block MDP per environment and transfer to a different block MDP. We also validate our results and demonstrate on a toy environment called Visual Cart Pole. This is the same as the cart pole environment from OpenAI Gym, except it uses images. These images of the carts and poles will differ in their colors, but other than that, they're the same environment. Once again, a block MDP. So model-free reinforcement learning without adaptation does fairly well at solving this problem. You can use what's known as domain randomization, which means you take, some large number of n source domains, train on all of them, and hopefully at that point you've learned that cart poles are cart poles and not random blobs of color. It can overcome any sort of adaptation. So notably, this can overcome transfer in dynamics. If your cart pole has a different gravity for every environment, but it also overcomes visual adaptation. So it should be able to see a orange cart pole and know that it's a cart pole. However, that adaptation needs to be coded in. If any of your factors of variation, so let's say you show it different colors of the pole but not of the cart, it won't work. You need to show it that any factor that you want to adapt to has to vary in the set of training domains. Now, this leads to very high sample complexity. The graph on the right for Coin and Run was released by OpenAI as a baseline with PPO. And you can see that it takes not 100, not 1,000, not even 10,000 training levels to really be able to generalize well to a new level. The line in blue is the training graph, and the line in orange is the testing graph. It's only really at like 30,000 levels that you actually get to be able to transfer. So that's probably not great. You can imagine that you don't really want to train your robot in 30,000 kitchens before you can transfer to a new kitchen. You can think about this as an integration over environments where you just show it enough kitchens that the specifics of each kitchen don't really matter to the policy. So this is a bit of a problem. So what's the solution? Let's go look at our deep reinforcement learning agent. It takes in a observation and passes it through a neural network, or any other machine learning model. We're with neural networks right now, might not be the case in the future, and outputs both a representation of a state and the best action to take. Of course, it really looks more like this. There's no nice image. It's just a array of numbers. And the neural network is actually split generally, and in the case of visual reinforcement learning, almost always into policy layers and convolutional layers. Once again, outputting the representation of the state and the best action to take. And it minimizes some loss function that varies based on the reinforcement learning algorithm you pick, but it maximizes its eventual reward. So the issue with this is that the representation that you use, as you can see on the right, the problem is conditioned upon the domain you're in. As I mentioned earlier, if you train this with the observations you see on the left and give it, the same exact environment, except the colors are different, it just won't work. We're conditioning upon the visual factors, and that's what I'm denoting as domain. So what's the solution here? Put simply, we'd like to learn a domain agnostic representation. Now, of course, this is much harder than it initially seems. If it was doing this by default, then it would transfer. So we have to do some new methods to get around this. Notably, we can take inspiration from optimal transport and look at the Earth mover's distance. This is a distance metric between probability distributions. It computes the easiest way to transport all of the material from one distribution into another, intuitively. Feel free at the question and answer session, and I can provide you with specific mathematical details. As I mentioned, it's an optimal transport plan between distributions, arbitrary distributions, so they don't both have to be Gaussian. They don't even both have to belong to the same family of distributions, which is very useful because we don't actually know what family of distribution our state representation outputs from our model-free reinforcement learning agent will be. As shown in the Wasserstein-Gann paper, this Earth mover's distance is both theoretically and empirically easy to align and succeeds in conditions where methods such as KL divergence minimization or total variance minimization fail. Furthermore, you can directly compute it. So you don't really have to, you can directly estimate it and directly compute that. You don't have to minimize some upper bound or something like that. So how do we actually do this? We can, from our output over convolutional layers, we have some feature representation that we want to be agnostic to domain. So instead, we can use an adversary that tries to guess the domain. And this is similar to the Wasserstein-Gann paper, this will actually estimate the Wasserstein distance between the two distributions of domains. The two distributions of representations condition the one domain. And then once we have domain agnostic representation after our convolutional layers, we can pass it to our policy layers, which will then, as earlier, output a representation of the state and the best action to take. Now, at this point, all of the information being passed into the policy layers should be agnostic to domain. So just as it can't, magically guess what domain you're in after not having any information to guess based on, this state representation will be domain agnostic as well as best action to take, which means the policy will actually not depend on whether you're on domain 1 or 2, your source or training domain. Once again, we can modify the reward function by adding a new term where we're trying to minimize the distance between domains. This is the L domain here. And we're trying to minimize the ability to differentiate between domains with the adversary, and we're trying to maximize the similarity between domains with the normal reinforcement learning agent. Once again, for additional details, loss functions, I can provide that in the question and answer session, or please refer to my paper. So, as always, we have to see what the prior work is, what was solving this problem earlier. Other than domain randomization, of course, which I mentioned, which uses, 100,000 different source levels before it can transfer. The first that we compare against is the current state of the art, or the prior state of the art prior to this paper. It attempts to learn a domain agnostic representation by enforcing Lipschitz continuity between different domains. What this means is a small change, such as a change in the background color, which doesn't really affect the policy, will have a small change in your policy. Now, this is not quite a direct minimization of difference between domains, and as we'll see, actually suffers from some problems. The other comparison is titled VR Goggles for Robots, and this takes a different approach. Rather than trying to align distributions of domains by training our RL agent, it will train an RL agent on the source domain and also train a translation network using a style transfer GAN, cycle GAN to be specific, to translate from target images to source domain state images. In other words, it translates to a known domain. This is where the VR goggles for robots comes in. It's like you put on VR goggles and then your robot is walking around in virtual reality. However, this focuses on a lot of irrelevant details. You can imagine that the background color of your coin run environment doesn't actually matter. The color of the hat that Mario is wearing doesn't actually matter. It doesn't really matter if you're playing as Mario or Luigi, but this will actually focus on that. And so as we'll see, it does well in simple environments like Toy Cart Pull, but it fails to scale in the ProcGen environments. Now, notably, all of these three algorithms have the same inputs. They have the ability to train in one source domain, which means it gets state, action, reward, and next state, and that's online, trained with PPO. In our comparisons, all three of these algorithms are built on top of PPO with the same implementation and tested on the same seeds. Furthermore, they also get images that are not correlated, not in a specific order, in a finite number from the target domain, and they have to output a policy that will transfer well to the target domain. So you can see on visual cart pull, on the left here, we have the baseline PPO that has no adaptation in pink, the robust domain randomization in blue, the VR goggles in orange, notably that takes in a pre-trained PPO agent, so it's a flat line rather than a training curve. That doesn't actually correlate with time steps of training. It uses a pre-trained agent. And WAPPO. So you can see that compared to robust domain randomization and PPO, WAPPO transfers far better. The green, the solid line is training performance and source domain performance, and the dashed line is target domain performance. So what we want is we want the solid and dashed lines to be as close as possible, but actually this just correlates to the dashed line being as high as possible, generalizing as well as possible. Notably, VR goggles does a little bit better, which makes sense. Visual cart pull is not a very visually complex domain, so a style transfer network is able to transfer extremely well. On the right, we can see visualizations of features. So from PPO and robust domain randomization, you can see that the purple features, which are target domain features, really don't align with the gray features, which are source domain features at all. The gray features seem to have a lot of variance, and instead the purple features seem to be more or less one number. So this indicates that there's not really a whole lot of alignment between the distributions. However, for WAPPO, you can see that the distributions are much better aligned. They seem to take on similar shape. While they're not quite the same type of distribution exactly empirically, it seems to follow a similar shape, which may indicate that it's similar meaning. And as we can actually see from the reward, this does indicate the meaning is similar. Now, of course, visual cart pull is just the toy domain, and we really want to look at ProcGen. So ProcGen comes with two different versions of each of the 16 environments, an easy version and a hard version. This really indicates the amount of variation between levels, the difficulty of each individual level. It changes a little bit per each environment. If you'd like details on how they differ, either please come talk to me on my poster session, or I can redirect you to the OpenAI ProcGen paper that describes it in detail. Now, what you can see is looking at each of the individual environments on the easy side, WAPPO actually matches or exceeds the performance of all of the other algorithms. And this normalized return graph shows the average across environments, where you can see it's clearly outperforming in generalization, which is excellent. Now, in the hard environments, these results are mirrored. Once again, in every environment individually, it matches or exceeds the performance of the other algorithms. And this is reflected in the normalized return, which is just, once again, the average across environments. So what are the takeaways here? Firstly, we've demonstrated successful visual transfer via domain alignment, distribution alignment. This means you don't really need some sort of additional thing built on top of your agent. If you train your agent with the right loss term, it can transfer between different block MDPs and different visual domains. Once again, as we've actually added nothing additional at inference time, it's just a change in the loss function. There's no additional parameters, there's no additional layers, no additional component, no additional pre-processing. It has the same inference time complexity as PPO or any other reinforcement learning algorithm you train with, which is very useful in robotics or any other real-time scenario. Once again, this work is complementary to work in dynamics or goal transfer that includes stuff like meta-learning or HIP MDPs or any other work. Once again, for a complete listing of that, please refer to my paper or come see at the poster session. And now we'll begin the poster session component, which I will be live for, so please feel free to come ask any questions. Thank you for coming.